In this lesson, we're going to explore the second law of thermodynamics. We're going to see if we can come up with a statement for that. And we're also going to explore the idea of entropy, or the concept of entropy, and try to figure out what that is and if we can calculate it. So first, let's answer this question. Which way does heat flow? And you guys know that heat flows from hot to cold. It always does. However, if we put a piece of hot metal in cool water, while we expect that the metal will cool down and the water will warm up and the temperature will come to some final temperature in between, the first law of thermodynamics does not require that. We could say that energy would flow out of the water into the metal, making the metal hotter and the water cooler. No energy would be gained or lost. It would not violate the first law of thermodynamics, but it never, ever, ever, ever happens. It's never been observed to happen that way. And so we have a second law of thermodynamics that says that's not the way energy flows. Instead of energy trying to make things more ordered, which in that case would make the water particles cooler and would bring them together so that they were moving less, instead things tend towards disorder. That is, energy always flows from hot to cold. There's actually several different ways we can state this, but all of these are valid statements of the second law of thermodynamics. Heat will not flow spontaneously from cool to warm. Heat energy cannot be completely transformed into mechanical work. We cannot build a perpetual motion machine. These two things kind of go together, and we will take a look at that first one in a little bit more detail when we look at thermodynamic cycles and heat engines, which convert heat energy into mechanical energy. And also, the last one, disorder increases through natural processes. Now, when we talk about disorder, it means exactly what you think it means. It means that particles become more randomly distributed, harder to distinguish. Everything is a little bit more spread out and a little bit more chaotic. So when we put a piece of metal into water, it is true that the metal cools down, which makes those particles a little bit less energetic and a little bit less random, but the water heats up, which makes those particles more energetic and more random and less ordered. And the net change is less order. And so what we do is we try to measure how much the order changed, and we do that with entropy. So entropy is a measure that indicates the natural direction of energy flow, and essentially it does that by figuring out disorder. So there's several different ways to talk about entropy. We can say that entropy is related to the ability to do useful work. Basically, as entropy increases, a system is less able to do work, and if you think about that, that's because work is the transfer of energy, and as time goes by, especially for like a thermodynamic system, if we have a hot spot and a cold spot, as time goes by, the temperature tends to reach equilibrium somewhere in between. And if there's no change, if there's no difference in energy, then heat's not going to flow and work isn't going to happen. So the ability to do useful work goes down. Another way of looking at it is disorder. The higher the change in entropy, the more the entropy increases, the more disorder we're going to have in a system. The second law of thermodynamics, another way of saying it, is that for every natural process, the entropy of the universe increases. Now that's sort of important that we're actually talking about the whole universe. So while it is possible to have a locally negative entropy change, that is locally more ordered stuff, somewhere else there's going to be disorder. And the increase in disorder is greater than the increase in order, which actually makes sense, and we'll look at a mathematical example of that in a minute. And by mathematical, that means we must have a way to calculate the change in entropy, or the change in disorder. And we do that by measuring the heat gained or lost divided by temperature. Now remember, temperature needs to be in kelvins, and heat gained is positive heat, heat lost is negative heat, which means we can calculate a negative entropy change. That means that the particles actually become more ordered rather than less ordered. This is valid only for isothermal processes, this equation, which means the temperature needs to remain constant. If the temperature changes, we have to use calculus so we can sum up the heat changes at every different temperature, or we can estimate fairly closely for small temperature changes by, instead of using that whole summation, we can just average the temperature and use that. And we're going to look at an example that does that as well. So our first one is examining the entropy change during an isothermal process when 0.25 kilograms of ethanol vaporizes at its boiling point of 78 degrees Celsius, where the latent heat of vaporization is 100 kilojoules per kilogram. Well, first, if we're going to calculate change in entropy, we need heat gain divided by temperature. Well, the temperature is easy. It says 78 degrees Celsius, so we're going to add that to 273 and get our Kelvin, which is 351, 351 Kelvin. And now we need our heat. Well, heat for a phase change is equal to mass times the latent heat of vaporization for this one. So we have 0.25, and this says kilojoules. I would like joules, so I'm going to take 100,000. So 0.25 times 100,000 joules per kilogram, and divide that by our 351. And if we work that all out, we get positive 71 kilojoules, not kilojoules, that would just be joules, per Kelvin. So 71 joules per Kelvin. That's our change in entropy. And it's positive, which is what we expect, because this would naturally happen at 78 degrees Celsius. If we had ethanol, it's going to vaporize, and that's because it's increasing the disorder. Because in a liquid, all those particles are fairly close to each other. They're all in the same relative location. There's forces of attraction that hold them there. That's fairly ordered. As they go to a gas, those particles are bouncing all over the place. They have random motions and lots of them, and that's disordered. So things tend to head towards this disordered state. Now let's take a look at an example where we actually have something increasing in temperature and something else decreasing in temperature. So a metal spoon at 24 degrees Celsius is placed in 1 kilogram of water at 18 degrees Celsius. The system comes to equilibrium at 20 degrees Celsius. So you'll notice this one actually doesn't happen at a constant temperature. There's 3 different temperatures, which means we're going to approximate the change in entropy by using average temperatures. But there's also 2 objects, and one of them is getting warmer and one of them is getting cooler, which means one of them is gaining heat and one of them is losing heat. That's okay. The heat lost by the spoon is going to be gained by the water because we're assuming a thermally isolated system. So let's find out how much heat the water gained. So the heat the water gained is equal to the mass of the water, which is 1 kilogram, times the change in temperature of the water. It went from 18 to 20, which is 2. Now, technically, yes, I should use Kelvin, but a change of 1 Kelvin is the same as a change of 1 degree Celsius, so that doesn't matter. And then times the specific heat of water, which is 4,186 joules per kilogram degree Celsius. And so if we multiply this all out, we get 837, yeah, close enough, 8,372 joules of energy. That's the heat gained by the water, which also happens to equal the opposite of the heat lost by the spoon. So the heat lost by the spoon, or the metal, or whatever we're going to call it, is equal to the negative of that, so negative 8,372 joules. Alright, so we know how much heat was gained or lost. Now we just need to find the entropy. Change in entropy is equal to the heat gained or lost divided by the temperature. What temperature are we going to use for the water? Well, since the water went from 18 to 20 degrees Celsius, we're going to use its average of 19, but we got to change that to Kelvin. So 273 plus 19 is 292, and the heat 8372. And if we do that division, then we're going to end up with about 28.7 joules per Kelvin. And it is a positive entropy change. Disorder of the water increased. The particles are now moving a little bit faster. Their motion is a little bit more random. The metal, on the other hand, had a negative change of 8372. Now, if these two are going to be the exact same change in heat, doesn't that mean that we should have the same change in entropy? The answer is no, because the metal was warmer for the majority of the time, which means its average temperature is a little bit more, and since the denominator of the fraction is bigger, the overall fraction is actually smaller. So the average of 24 and 20 is 22, and we add 22 to 273 and get 295 Kelvin, and we divide that out, we get negative 28.4 joules per Kelvin. So we can see a negative change in entropy, which means the particles actually slowed down and became more ordered, and the change in entropy was negative. But we did not violate the second law because the net change is actually still positive. 28.7 plus negative 28.4 is equal to 0.3 joules per Kelvin. So the net increase in entropy is positive, just like we expect it to be, because for every natural process, and putting a hot spoon into cool water and having the temperature come to the middle is a natural process, we expect the entropy to increase.